Hi. Okay, hello. My name is Mario. He's Gorka Irazoqui, and we're here to talk about the case against using TEES in your crypto project. We work at Spectre Labs, and for a little bit of context, we've been building Witnet for the last years, which is a decentralized Oracle network. So the question is like, why are we here? I think it's pretty obvious, but let's say it. So because privacy is important. At least most of the public blockchains, obviously smart contracts are deployed and called publicly. It means everything is available for anyone to watch it, to snoop in, and we cannot use, obviously, private inputs. There are many cryptographic workarounds that have been there for several years, like sticky snarks or homomorphic encryption. But we are here about to talk about the TEES, the promise of a perfect solution. So after explaining a little bit the TEES, we'll continue defining or showcasing some hardware attacks. Then we plan to have a demo of a Spectre, but unfortunately it doesn't work on Linux. And we will finish the presentation with some use cases in the crypto space and some conclusions. So the promise of a perfect solution. So TEES stands for Trusted Execution Environments, which are simply a secure area in the hardware that aims to provide confidentiality. It means having data encrypted and also integrity. It's trying to avoid that anyone can tamper with the data. So it's really important to say like these areas in the hardware are really isolated from the non-trusted world, such as applications or operating system, and they have different names depending on the manufacturer they build the T. In the case of IRM, it's Trust Zone. These were one of the first ones. And we also have Intel's with SGX, they are well known, and EMD Secure Processor. So, one of the things that TEES provide is encrypted isolated memory. In the case of Intel, it is called enclave page cache, which is just a specific part of the RAM memory that is being encrypted with a hardware key. It's being used in the well-known AES encryption, and the idea is like in the memory and in the memory bus, in the RAM memory and the memory bus, any attacker can really snoop in because it's encrypted, and obviously he cannot really see what the flow of the data, what the data is in transit. And this boundary finishes at the CPU. So maybe we have already a hint, like maybe an attacker will try to use this after the CPU. So another thing that are really important for the TEES are the attestations. First, the local ones. This is just two different applications to prove themselves or to prove one to another that they are running on the same platform. The flow is really simple. It's based on a challenge response simple protocol that the one enclave sends a request to the enclave to application A that is running in enclave A, and the enclave asks the hardware to produce a report that contains some information about the build, some logs of the enclave, how it was built and how it was initialized, and it's signed by a symmetric key provided by the hardware. Later on, it's sent back to the enclave B, and it can also ask the hardware to verify those reports. Then the next one is the remote attestation. It's similar, but here it's using a special enclave called quoting enclave in the case of Intel. In this case, this enclave uses an asymmetric key that's issued by Intel. It's called the IPID key. And the flow is similar in the way like there is a challenge response. Imagine we have a challenger that is outside of a platform and it wants to verify that some application enclave is running in a specific hardware. For that, he sends a request in the same way, the application forwarded to the application enclave. Then in the point 2, what we have is the local attestation. So the enclave, application enclave and the quoting enclave, they have to prove that it's running on the same platform. And if it's the case, then the quoting enclave will sign this report using this Intel key, which is in this case asymmetric, and it will be forwarded back to the challenger. So once the challenger receives this report, either he knows some public key to verify this report, or maybe he could also ask or request a third-party service from Intel, for example, to verify that this report is correct and valid. And the other thing is, like with this, what we can do is like we have communication from the outside world. Imagine we are generating asymmetric keys within an enclave. So it's obvious, like an external client could send data through an untrusted channel and an untrusted operating system using this asymmetric key. So it's open many use cases that can be used. So now the interesting part is the hardware attacks. Before starting, so why the T's, why these enclaves? The idea is really basic, and it's just to decrease the attack surface of an application. So normally, without enclaves, we know that a malicious user may try to exploit the operating system or the virtual machine manager. But in the case with enclaves, this surface area is reduced to a portion of the hardware and the application layer. So going straight to the point, so what are sidechannel attacks? These attacks are those in which a malicious user tries to use a covert channel, try to analyze some physical behavior in order to extract some information. The idea is, some examples are trying to analyze, for example, the power consumption, the electromagnetic waves, some acoustic, for example, some noise that the hardware is doing, or perhaps the execution time, some algorithms or some code, or even the thermal. The idea is like to gather information that may seem as noise at the very beginning, but then they can try to infer some confidential data that is it's ongoing, no, in the code. So this, for example, there is a famous case that is the Trezor one that suffered one of these attacks. And here the takeaway is like, do side channels really always need physical access? So during this presentation, we'll showcase that not really. And this is the start of our concerns. So in a context in which we have a micro architecture, like for example this one from Intel, an attacker may try to exploit or to infer information from the different of their components. And the sad reality is like, during many years, most of the manufacturers, they have been focusing on trying to make their architectures more efficient, but disregarding some security concerns. This, all of us, we know the race there was with the CPUs, for example, between Intel and AMD. But anyway, that's what happened, and now it opens some vulnerabilities to be exploited. And this is also applicable in some other contexts, like for example, imagine cloud, in which you are sharing some hardware, or even smartphones, or in the case of this presentation, the trusted execution environments. So I leave the floor to Gorka.
All right. Thanks, Mario. Yeah. So that was a very nice introduction on how can we, we saw some microarchitectural components that could be exploited that actually share between the TEs and the normal processes that are hosted in an operating system. So let's go one by one to see what can be exploited and what cannot. All right. So the first one that we're going to review is caches. All right. So basic caches are just small pieces of memory that are put between RAM and CPU so that you can access data faster, right? So basically they hold recently accessed data so that you can access that data faster. Usually we have a multi-level hierarchy. That means that usually we have some caches that are, some cache levels that are private per core, and then we have like a shared one, at least the last level one usually shared across cores. And also some interesting things. The first level usually is divided into the data cache and instruction cache. That means that the data cache essentially holds data while instruction holds instruction. Oops, sorry. I did this yesterday as well. So how do we decide, or how does the CPU decide where to which location does an address go, right? So it's addressed by the physical address. So we take the physical address, and part of it we use it to select where to the cache that piece of memory goes, all right? So there's usually caches are divided into sets. We can think of them as buckets. So basically the physical address, one portion of the physical address decides to which set that memory goes. So let's go to how an attacker can infer information from the cache. So essentially, for the record, let's try to assume that the attacker and the victim share some kind of memory. Although this might sound a bit strange, that's usually the case when we launch like two processes in the same operating system with something that is called kernel share same page memory. So it's not that strange. So essentially, if we assume that attacker and victim are sharing the same memory pieces, when I used to do these attacks, what we used to do is just take the entire instruction set architecture definition and look for like nice instructions. And one of them from Intel was CLFlash, right? So CLFlash, what it does is it takes a memory address and flashes it from the cache hierarchy. That means that if, again, the attacker shares the memory piece with the victim, the attacker can just make sure before the victim executes its code that the memory piece he wants to monitor is out of the cache. And then if the victim actually utilizes it or not, if it utilizes it, it will actually load the data again to the cache. And the attacker, what it's going to do is measure the time it takes to access that location, that memory piece, since he has access to it. What he's going to see is that the cache accesses are around 100 cycles faster than RAM. That means that he can infer whether the victim utilized that memory piece or not. How do we measure those 100 cycles? It's usually hardware providers put some registers there so that you can count cycles. Great, that was very nice, but the shared memory assumption sometimes doesn't hold, and sometimes we want to attack something that is not shared with the victim, so how do we do this? Well, essentially, the attack is very similar, but this time what we're going to do is, assuming that we know to which set the instruction, for instance, that we want to monitor goes into the cache, what we feel is that set. We trash the data, here represented with the green memory blocks, and then we just let the victim access the instruction that we want to monitor or not. If the victim accesses it, of course, since the set was full, the victim is going to throw away one of our trash addresses from the cache, and that means that when we measure the time to reload our trash addresses, 3 of them will come from the cache, and we can measure it, and 1 of them will come from the memory, from which we can infer that the victim utilized the instruction we want to monitor. So how does this translate to an actual attack? So this is the algorithm that was implemented for RSA in NuPG not that much ago, like 5 years ago. And as you can see, I mean, the important thing to notice from here is the fact that it takes the secret key and it goes bit by bit. If the bit is a 0, only a square is executed, and if the bit is a 1, a square plus a multiply is executed. That means that so essentially we call this a secret dependent execution, because it depends, the execution of the program, it depends on the secret that you input. Imagine that we can, with the previous attack or with any of the previous attacks, imagine we want to monitor this instruction or these ones, right? In this case, the graph shows the monitorization of this instruction. And what we see is that when the bit is a 1, of course, we see more time between these 2 squares. All right, so basically, the utilization of this one basically depends, or the time between executions of this instruction depends on whether the bit is a 0 or 1. So we can reconstruct the entire key like this. Great, that was for caches. So caches are attackable. What else is attackable? There's something very cool in the CPU which is called branch prediction unit. It's essentially a piece of hardware that tries to predict the branches that you have in your code, so tries to predict the outcome of the branches you have in your code. And yeah, they're not that different from caches in the sense that they are finite in size. And yeah, so basically the way to attack it is very similar as well. So branches have a specific position, usually in branch prediction units. So if we know the branch we want to attack, in this case, imagine the same one as we had before on RSA. So what we do is couple of things. We first need to understand the branch prediction unit, how it works, right? So, for instance, there were many branch prediction units in the past that predicted if the branch wasn't in that buffer that holds the predictions, actually, the branch was predicted as not taken, all right? And it wasn't inserted in that buffer until it was mispredicted. So as long as it was predicting it well, it wasn't actually adding it into the buffer. So taking those two things in mind, so what we can do is have a trash branch always calling it, always taking it. So we have our own branch that goes into the same position as the target branch that we want to monitor, and we always take it. All right? So what's going to happen? If the victim uses that branch, what it's going to do, it's going to kick out our branch from the branch prediction unit, and the next time we call our branch, what we will see is a misprediction. Why? Because it is predicted as not taken, because it's not in the buffer. So we can measure that, and that is going to force a CPU rollback, or sorry, a pipeline rollback. Yeah, that's measurable, and that leaves like a 20 cycle difference between one and the other. So with those two things, we can understand very well those two things, and the one I'm going to explain, we can understand very well what happened with the Spectre and Meltdown attacks that were actually very famous. So yeah, what happens when a branch, for instance, is predicted as taken or not taken? Well, what's going to happen is that the CPU, as we said, is going to execute the instructions that follow that branch. Speculatively. So basically, it's going to execute instructions without knowing truly whether it needs them or not. All right, and then, of course, if the branch was predicted wrong, that pipeline execution has to be flashed. So, but the branch was just an example. There are many other cases in which that happens. We will see it later. But yeah, the branch is the one. The branch speculative instruction is the one that the Spectre attacked. So how does the Spectre attack work? It's very easy understanding the caches and the branches. So we first have, let's imagine that we have in our victim code a branch that looks like that, all right? So we have a branch in which we can insert, let's assume that X is controlled by the attacker. So basically X is an input to the code we want to attack, for instance. And we have a typical buffer overflow countermeasure, which is if you want to access an array, first of all, check that the input actually fits the array. So yeah, what the attacker can do is essentially call that instruction like quite a few times with the right X length or size, so that array is actually always taken. All right. So basically, I train that branch so as to be taken all the time. And then suddenly, when I know that the predictor knows that branch should be taken, I just change the X to insert an X that is bigger in size than the array that we want to access. So what's going to happen in that case? In that case, the branch is going to be predicted as taken, as it was set by the branch prediction unit. And that instruction, the second one, is going to be speculatively executed. So basically, it's going to access a memory location that we shouldn't have access to. And that obviously leaves traces on the cache. And if we monitor the cache to see that instruction happening before it's rolled back, we actually can access locations, again, that we shouldn't have access to. Meltdown was very similar to Spectre, but it exploited another kind of speculative execution, which is when you try to access a forbidden region, so a region that you don't have access to, literally, just put in an address that you don't have access to, the CPU, before checking whether you have permission to access that memory piece, it actually loads the memory piece. So it loads the memory piece, or it loaded the memory piece, and then check whether you had permission to actually access it. Of course, if you didn't have access, it rolls back. But by that time, you can already see the effects on the cache, and that means that you can actually dump the entire memory of another process, including a process running in a team. So yeah, a couple more attacks. So we saw how speculative execution can be attacked, how caches can be attacked, how branch prediction units can be attacked. This time we're going to see how port ports can be attacked. So essentially, ports are just ports to which microoperations are sent. So basically, your computer is translated into your software is translated into microoperations, and then it's sent to an scheduler that assigns those instructions into different ports. But the problem is that this balancing, the scheduler doesn't balance. Not the scheduler per se, but some ports have specific instructions that can only be executed in that port. So that means that if we find a secret-dependent software, or if we're running a secret-dependent software again that uses one of the ports, depending on whether the secret is A or B, we again can generate contention on the port so as to see whether the victim is actually utilizing the port or not. Again, measurable in time, and again, potentially leading to full secret leakage. And then the last attack that we wanted to cover here are a bit different. They're called fault attacks. They are not sidechannel attacks. And we haven't seen many in SGX or in ET, to be honest. But recently there was a paper that actually executed one of these in a very funny way. So fault attacks are just attacks in which we just induce an error in the execution of an instruction. It can be because, we increase the voltage so much that it leads to an error or whatnot, all right? That can, if you're running something like AES, that can lead to the key extraction. Why? So if we have the same plain text, and we got one of the ciphertexts, and we got one faulty ciphertext due to some external attack that we have made, we can execute fault analysis, and that gives us the key. So the attack I mentioned that was proposed in SGX was called Plunderworld. It's quite recent, so I encourage you to read it. So it actually, there's a very funny register to which if you have kernel access, which is assumed by the attacker model of SGX, for instance, you can actually touch a register that is called, it's the MSR register. I don't remember what they stand for, but so essentially that actually allows you to change the voltage of some components by -1 or +1 volts. So an attacker essentially it's doing the following: an attacker learns about how or at which voltage the CPU faults, and when someone, for instance, the victim is using ASNI, for instance, the attacker sends that voltage before completing the encryption, and he gets the faulty ciphertext. Again, this wouldn't be a problem, but the fact that we can see the results that more significant bits are flipped, which is actually something quite predictable, or else 1 to 5 continuous bits are flipped. And we had a demo. It's a pity that we cannot show it because obviously installing SGX, I don't know if someone has installed SGX drivers in his computer, but you guys know if you have, it's a pain in the ass. So I had it installed in my computer, but it doesn't work because it's a Linux computer. So I can show it later if someone wants to see it. But it's a pity that we had to skip this actually. So Mario will speak now. Oh, sorry. Mario now will speak out some use cases.
Okay, so let's continue with some use cases in the crypto space that I'm pretty sure some of us already know them. So the first one is about confidentiality. The idea here is if we can create an asymmetric key in a T, for example, obviously we could use this in our benefit in order to send, for example, to a smart contract some private inputs that only the T can decrypt. The typical example I hate is a flight insurance smart contract in which, for example, Alice wants to cash out some insurance money and she doesn't want to disclose which flight she was going to take. So for that, she encrypts the data with some asymmetric key that lives within the T. And obviously, it is the only one that can decrypt it. Then it will do the query to the API in a secure way, for example, using TLS. We know some projects do that. And then the result can be in plain text, without ciphertext, and then she can cash out. So here the problem, as Gorka said, is like we don't know for sure if there could be some side channels attacks that may infer some information that is in transit. So, and the same, some fault attacks may also lead to some key extraction that will invalidate the complete scheme. So the other use case could be for key management. We know these are a piece of hardware. We know hardware can generate random numbers with much better guarantees than software. So why not use that in order to generate, for example, some cryptographic keys? Imagine we can interact, maybe we can generate some passwords in the T that are from other blockchains. In that way, we could using our credentials in some blockchain, we could interact or sign transactions towards other blockchains. Here is the same. If we cannot be sure that there could be some attack, if there could be some attacks, such an attacks in the T, maybe the random number can be inferred in some way, really endangering all the funds, no? In this case, in the case I mentioned. And the last one is similar to the previous one because it also relies on the hardware random number generator, and the idea is like to use it as public beacons. We know there are many platforms or systems, they would like to have some sort of committee selection being done in some random way, and for that is a really nice use case. Here the impact of the attack is not so high, but obviously a fault attack may reduce the entropy, and maybe there could be some prediction, or you can decrease you can predict which random numbers are more probable or not. Okay. We'll manage. Okay, to finish, some takeaways. Obviously, during the last years, we have seen that there are increasing number of attacks on hardware. So that doesn't make us sleep well, to be honest. We know these, they are not the perfect solution as it seems, not because they are not great, but because they are not, for example, they don't make us code better, and maybe they have not been fully audited. So maybe here's a food for thoughts for manufacturers. Maybe they could, in the future, I don't know if we will do, think about some redesign, having more security concerns in mind. However, we know this may be super nice for some use cases, but one size does not fit all. The good part, as always, is like, because some of these security concerns, they are super nice cryptographic protocols that have appeared in the last years, like Deco and Mixicles. And yeah. And just to finish, as I mentioned before, we come from Witnet. We are building a decentralized Oracle network. And many times we were asked why we don't use these. And here the answer is really clear, because it's we really don't need it, in the sense like we are building a centralized Oracle network that is completely trustless, is permissionless, and our security model is based more in cryptographic sortation. It means having a high number of nodes that will be assigned randomly to execute some task. We can understand this better with the diagram. This is the life cycle of a data request within Witnet. The first stage is the data request definition, how data should be queried, aggregated, and tallied. It means converting it from several reporters into one single data point. The next one is the commit phase, in which all the nodes from the network, they will compute by themselves if they are eligible to execute this task. And they will do it using VRF, a verifiable random function, that has an input also the reputation they have. So the more honest they behave in the past, the more odds they will have to execute or to be assigned to a task. Then they will follow a commit reveal scheme. It's just sending a commitment and then sending a reveal transaction with a result. And finally, once we have the results from all the reporters, there will be another transaction in the next block, that is the tally, in which, in this case, a miner takes all the results from all the reporters, applies a deterministic function that reduces and aggregates the results into one single data point. And that's all. Thank you very much for listening. If I took your interest in something about oracles, we have tomorrow a talk about Radon, which is a domain-specific language for oracles. So thank you very much. And questions, obviously.
Yep.
Yeah, thank you for the presentation. So given that we can expect a lot of nodes in whatever decentralized network we have are actually running on shared execution environments in like virtual machines, for example, on AWS or GCP, isn't something like trusted execution environments like SGX still raising the bar, so to say? Like, it's not an impenetrable fortress, but you're still, when used as like a layer defense strategy, it's still raising the walls for penetration. So I would argue that if you have the possibility, you should still use it, not as an alternative to something else, but as a complementary in security.
That's a very nice, thinking, or line of thinking. I tend to disagree, but basically because, like, when you assume that you're executing, for instance, two virtual machines in the same hardware, you assume that the virtual machine manager, the operating system is not going to be malicious. It's much harder to attack. So when you don't have control on how tasks are scheduled to the victim process, in this case, an attacker process, that's a very hard, let's say, a scenario in which we can attack. I mean, it is attackable still, but probably the number of traces that you would need to infer a key is much higher. In the Ts, that changes. So if in a T, I'm assuming that there's some malicious guy that is offering some kind of isolated hardware piece that not even that malicious guy can tamper with. So since he's in control on how things are scheduled in that case, it allows for like much fine-grained attacks, which essentially with one or two executions you can get.
I'm guessing like not as a defense to the hypervisor, but to neighboring VMs, for example.
Yeah, sure. In that case, would work. Yeah, I mean, we're not like against T's in all the scenarios, but there's some scenarios in which if the person especially if the person you're utilizing the TE for, like, is untrusted. Like, it's not the case in this case in AWS, for instance. But if I have a decentralized protocol that I'm trusting, like just random people I don't know that are offering their TEs to execute the stuff, in that case, I think it's quite dangerous. Any more questions? All right. Thank you so much for attending.